be. I'm located out on the West Coast. Right now I have a group of my fellow consultant engineer specialists. We'll go right around, and we're all here for any questions that you may have. I got Diksha. She's located out in the Midwest. I have Matthew Wickham. He is on the East Coast. Robert Angst is East Coast, Southeast Coast, Southeast. And I have Richard Purcell, who does the
Atlanta, yes, Southeast.
So today we're going to give you a quick overview of breaker basics. I'm not sure what level of competencies you guys have on breakers, but we're just going to talk about how breakers work and what they're used for in their application. We hope that you guys have any questions. Please feel free to write in on the question pane. I will get to it as soon as I can. We'll probably have a Q&A, live Q&A at the very end. And hopefully I'll have all these smart guys with me to help me along as we go through this presentation. So I think you guys are still coming in. It looks like we got about 300 people. So I'll start it off. Okay, so breaker basics. I'm not sure if everybody knows what a breaker is. So we're going to cover the product fundamentals, the applications that we use them on, and the electrical standards. A circuit breaker is a device that is designed to open and close a circuit using a non-automatic, which is a manual means. As you can see, most circuit breakers have switches on them, so you can walk up to the actual breaker, flip a switch, and you're basically disconnecting power to all devices down the line from that breaker. It also has the ability to trip or automatically open the circuit based on overcurrent levels without injury of anybody being around. So if you have any kind of short or an overload, and we'll talk about the different types of faults that you may see down line, this breaker is there for safety for both the person and the equipment, where it will open up and make sure that all power is disconnected and service can be done down the line from the breaker. Basic parts of the breakers, as you can see, we have an operating level right here. This is your manual on-off switch. A nameplate you'll find on all breakers, basically giving you the current ratings and all the rate voltage ratings that you have on the device, so you know exactly what you're looking at. Terminals are usually where the power comes in and the power goes out to down your line devices. An arc chamber, now one of the things that we know is that when you open up a current switch or a breaker, you do have an arc going between the two contacts. We have moving contacts and fixed contacts. As you open up, you will experience an arc flash. We do take that into account, and we have these arc chambers that are designed specifically to make sure that the arc flash is extinguished as quickly as possible without any damage to our breaker. And finally, we have our trip unit, which you can think of as the brains of the unit. This allows you to set your trip curves, your trip levels, your current levels, time delays, and all other parameters that you want to put in the breaker. Basic ratings that you'll see on breakers are the current, which is usually referred to as frame size. There are various frame sizes that you can have. Continuous rated current, that means that's the current that can go through the breaker without causing any problems to the breaker or to the load. Basically what size of load that you're having, such as 800 amps, 1,000 amps, or what have you. 2,000 amps is usually the maximum that you're going to see. And then a maximum interrupting rating. This is basically the most current that this breaker is going to allow onto itself before it opens up and makes sure that the fault or whatever issue happened to cause the spike in the current is now safely extinguished. Voltage rating is, of course, the input voltage, around 480, 277, or 120, and that is the supply that you are bringing into your building. So how does a breaker work? Non-automatic manual operation is just using a lever to open the breaker. So as you see, the power comes into our terminals here. We will go through normally through the arc chamber into our fixed contacts. The powers then go through and the current flows out to your branch or your circuits and all the products download. When you flick the switch, you'll notice that our moving contacts pull off, which then disconnects the circuit completely from the power coming into the building. This means nothing down the line has any more electricity, there's no more current, there's no more voltage, and it's safe to be, you can use it to perform maintenance, or you can go and find out if there's any damage to your products down the line. Automatic means that you do not actually have to touch the breaker. Now, this is what we considered a very useful safety feature. And what we're showing on the side over here is your basic trip curve, which is a long delay and then an instantaneous delay. We'll get a little bit more detailed a little bit later in the presentation about these. Basically, what you see is on the x-axis is the current. This is logarithmic scale. So this is as the rated current, so 10 times the rated current. On a long delay time, you will have this much time, whatever seconds that may be, or milliseconds, as it were, before the breaker will automatically trip. Now, these are all settable, so I can push this curve out a little bit further, which would mean that I'll have a longer time at 10 times the current rating before I would trip. Instantaneous, again, is as soon as I see 100 times my current rating, I'm going to pop automatically. There's I believe a 2 millisecond time delay when we see this instantaneous rating. So some of the causes of this overload of this automatic current protection overload condition, that means that we have a load somewhere down the line that is just pulling an extraordinary amount of current, not what it's rated for, not what you want to have happen. This can cause danger in heating, it can cause fires, it can cause damage to your equipment, and it also puts your people into a dangerous situation. This is your first part of the trip curve called the L for long time delay. What we allow is for an instantaneous spike. So if you are at 10 times your nominal rated current, you can pull in, say, you have a motor or something that's a heavy current when you're going to get a real sharp spike in your current. You can go for a couple of milliseconds without tripping the breaker. This is normal use. You'll see that on big turbines and motors, but you won't trip the breaker. However, if that load keeps pulling that amount for a longer amount of time, that's when we trip. So during the overload, the excess current will go through the breaker and generate heat. The greater the overload condition, the greater the heat, the higher heat, and we trip it. How does this work? Well, what we have is called a bimetallic element placed into the breaker. This has two different metal alloys in it, very proprietary combination. We can't tell you. We have to make sure that you sign an NDA. And basically, one of the metals will expand quicker than the other. This causes a deflection in the element. That element bends, and you will see that it trips. Again, if you look, the heat is heating up those bimetallic elements right down here in the box. And as they get hot, it bends and it opens or moving, therefore disconnecting power down the stream. So if you have one of your loads that maybe is misrated or is starting to pull too much current, you don't want to get too hot, and so that this this mechanism will trip. Again, you have a long time delay because there will be spikes in the current on certain loads, especially inductive loads, and we allow for that spike to come in as long as it's a quick spike without tripping it. The second one that's most important is the short circuit protection, I like to call it. It's an excessive current condition when the phases make contact or you have a short to the neutral or ground. Correlates to the second part, which is called I for instantaneous, and these trip curves are pretty much across the industry standard. So you'll typically hear an LI, sometime an LISG, and these are just different portions of the trip curve that tell you what fault and how long it takes us to trip and open the breaker. During a short, the current can flow 1,000 times greater than the normal operating current. So I think if anybody's been in the industry and has ever touched phase to neutral or two phases together, you see the big spark and everything pops. It is instantaneous. Well, that's kind of a misnomer because we do have about a 2 millisecond time delay before we actually trip. And that's just the nature of the physics behind how we trip using the magnetic fields that we are sensing the current going through. So this magnetic field, again, is going to be in here, and what it does is it requires this plunger, which is basically just a metal rod inside of an electromagnet. When the magnet starts getting charged, it's going to force the plunger down, which then again moves the contact out, opening the breaker. So I don't know if you can see that. That happened rather fast. That's why it's instantaneous. It's not a warm-up of the metal. It's as soon as the induced magnetic field is there due to the overcurrent, which is very quickly. The plunger shoots out, pushes down our movable contact away from our fixed contact and out, and we kill power down the line. You notice that it all goes through this arc chute because as that current's going through and these two contacts pull apart, you will see an arc flash. Again, when our arc chutes are designed particularly to deionize the air that's around it, absorb the energy without much damage to any of the contacts or any internal workings of the breaker. The other curve that I mentioned just before was the S curve, so this would be considered an LSI curve or an LSI breaker, and it stands for the short time delay. So again, this is for when you know that you're going to have an instantaneous spike because of the load, whether it's being inductive, high resistance, it's going to spike. But again, you want a little bit of a time delay because you know that every time you start that motor, you're going to see the spike. If you didn't have this time delay, as soon as it hit the instantaneous level, it's going to pop. Right about here, you can see that you're going to absorb that large spike, and you'll still be running perfectly fine without any interruption of service. It's typically used in the selective coordination applications, and that basically means if you have more than one breaker, so you have a main breaker, and then a branch breaker, and then a feeder breaker down the line, if you select the S breaker at the closest to the service at the longest time, it can absorb a large spike without popping. Then as you get closer to your equipment, you're going to make the time delay a little bit shorter and shorter so that when you do have that fault, it happens quickly at the breaker closest to your equipment. So then you're not shutting down the whole entire branch, you're just shutting down that breaker that is by the equipment. This saves a large time on startup and shutdowns, and in an application such as the mines or any place where you're doing a high yield over time, even blowing a branch and shutting down 3 conveyor belts is a lot more expensive than just shutting down the one where the fault happens to be. So the automatic means, you're going to see a lot of these curves all over the industry. As you notice, you have 3 curves in this one example. You have the L into the I, here, here, and here. Our breakers allow you to choose which curve you want to employ. So even though you have an 800 amp rating, you may want to have a shorter time delay on an incoming current. So you would choose this L curve and this instantaneous so that when you hit the spike very quickly, it's going to shut off. However, if you know that the spike is going to be coming and you need a little bit more time to let the spike cool down or get to the motor so that the load warms up, you can pick the long curve over here, and you can see that your operation will keep on going at this spike for a longer time before the spike actually reduces itself, and then you'll keep on running for the life of the circle. You can actually set the different levels for the L and the I based on, you know, whatever you choose. So you can choose an L curve that's way up here, saying that I'm going to have a long time delay before I have to trip, so I can take a lot of current in an overcurrent situation, but my instantaneous is going to be either here or here, so that as soon as I get past this instantaneous, I'm braking. But I'm going to allow this long time delay at this current level. Now, if I didn't want to trip that early on an instantaneous, I can choose this instantaneous on the same long curve. So you still have the luxury of getting that spike here. The spike can come down, you'll be in fine operation, but once you hit this instantaneous, it then pops. So again, this is very useful when you're doing selective coordination, but it's also useful when you understand the application you're in, the loads that you're seeing, and the actual current form that you're going to be seeing, whether it's a large spike, long time delay on the current draw, or if you're going to be seeing a choppy current time and time again. A maximum interrupt in grading is the maximum current level the breaker can safely interrupt when applied within its rating. Basically saying that if you go 1,000 times the current rating of this, say 800 amp breaker, if you go past that, we're going to open instantaneously at the 2 millisecond mark right here without any damage to our breaker. However, if you go past that line, we cannot make that same statement, because you are exceeding the maximum current level. This is something you don't want to do because it can result in catastrophic failure in both the breaker and the equipment down the line from the breaker. So as you can see, it's very important as you are looking at these breakers and speccing out these breakers to know exactly what load and the application you're looking at. Again, if you're looking at a spike, you're going to employ the L, and then you're going to make sure that your time is fine before it levels off, and hopefully your current stays below the instantaneous. Goes above the instantaneous, we're going to open right away, and if you go past even our maximum rating, then we're all in trouble. So it's very important to look at the ratings, both the voltage ratings and a maximum current level. Generally, I like to recommend you want to stay 80% below or 80% of the maximum current rating. So if your normal rating, if your normal current is going to be around, say, 800 amps, you would pick a 1,000 amp breaker, and then you will be running safely below this mark on your breaker. So some product fundamentals. When we get to this arcing, you can have a high let-through of energy. I squared T is the levels that can result in thermal damage. This is more of the arcing. So if you think about it, time can be low, but your energy can be high because I is squared. This is the square law of the current coming in. This is going to cause thermal damage, mechanical stresses. Basically, the challenge for the breaker is to make sure that we extinguish the time as quickly as possible, therefore letting the let-through energy as low as possible. Let-through energy can get past the breaker because, again, these things happen very quickly, and it can cause all sorts of stress down the line. So magnetic forces are created. This can cause bus bar bending. This can cause wires. I don't know if anybody has ever seen high voltage wires that are having issues and they kind of bounce around like snakes. What we want to do is we want to stop that, again, for the safety of the person and for the equipment. UL turning limiting substantially limits the peak let-through. So UL has a standard that says we will not let this go through at this much energy go through at this time. This means less than half a cycle of the input. So as everybody knows, power coming in comes in as a sine wave. You have a positive cycle and a negative cycle. It has to be left at less than half the cycle. They do not want to see a full wave go through with this energy because your time is double that, which really increases the amount of energy that's going to be seen down the line. Typically, our breakers do it in a quarter cycle, which is usually a little bit better than the industry average. So we do limit that current, we limit that energy, we cause more safety down the line. ABB has UL current limiting breakers and the T-Max and soon to be the T-Max XT breakers. And basically we use those for feeder devices in UL 508 control panels. It's for the sensitive loads. So if you think about data centers or anything where a high peak or high energy, a spike in current, any kind of voltage spike, it can cause damage to these, which is costly, time consuming, and not the easiest to repair. Using breakers in the right way with the right settings for the trip curves, and if you do coordinated selective coordination, which is using the right breakers down the stream, you can reduce the amount of damage, the amount of downtime, and the amount of maintenance that is required on your equipment. Plus, you're also getting a very higher level of safety for all the people that are involved maintaining that equipment. As we alluded before, selective coordination minimizes the effect of the electric fault, ensuring that the breaker closest to the equipment is the first to pop. So in this typical example, you're going to have a large breaker that's taking in the power from the utilities or from your branch. We have a secondary that might have a couple of sub-branches coming off, such as the T1s going over here, where you have only 125 amps coming in, and maybe you have another one at 125 amps. Now, if this load down here has an issue, you don't necessarily want to take out the main breaker, because when you do take out the main breaker, you are shutting power to all the equipment down the line from there. So you can have several different engines, turbines, conveyor belts, what have you, coming off of that breaker. You don't want to stop 5 lines because of a fault on one. So you would choose lower breakers and put them closer to the load so that if one conveyor belt has an issue, only that conveyor belt will pop. As you can see, they're setting the trip currents so that the one closest to the load, closest to the conveyor belt in my example, will be the first one to pop. So if I'm at, say, 1 times my nominal, you can see that T1, which is this tiny little breaker, that's going to be your almost your machine breaker, if you will pop before T5, the T5, which is our branch feeder over here, pops. This means that any other equipment that is coming off this T5 will be running just fine, and all you lose is the downtime from this one conveyor belt. We have several different configurations that you can mount the breakers in. We have fixed, which is a bolted connection, cable lugs and bus bars. Breakers mount into the equipment of the enclosure and will not be removed without de-energizing the system. Now, one of the big safety features that we have in our breakers is that we have an isolating wall, so that when you do take out the breaker, you will be shielded by a wall that keeps the live bus bars away from being touched. This is very significant because you don't want anybody putting their hands in there and being exposed to the service line. The currents there can cause real big problems. The other types we have are plugins. This is an assembly that requires quick change, so if you have any kind of fault or if you need to up the ratings or change the ratings, you can pop it out and pop in another devices. They're generally used for the T-Max breakers. These are field installable, no racking mechanism needed. Again, it's just a simple pop in, pop out. These are going to be the devices that you're going to see close down the line on the branch circuits that are going to be protecting your equipment. We have the mounted configuration of a drawback. This does require the racking system, which means that you have to have the breaker and a cradle, and you must rack the breaker into the cradle where the power is coming into. Again, this is where our isolation bolts are very important, because as you have your bus bars carrying the service 600 volts or what have you at an extraordinarily high current, this is something you don't want to expose anybody to. It doesn't matter how much PPE or personal protection equipment you are wearing. It's a very dangerous situation. So what we have is the shutter walls will keep you isolated until the breaker itself is completely racked in. So this is just a safety feature that we have on our breakers. It's widely used in critical power. So again, it's something that you don't want your power breakers to go down. You need that power all the time. Any second and any minute that you are losing power, you're losing money. And typically our customers don't want to have that. You can have it on the T4 through 7, which are a little bit bigger breakers than the small ones that we showed beforehand. A little bit bigger than these guys. And they have better ratings on that. You have a lot of different accessories that you can put into these breakers, which allow for a lot of different applications. An undervoltage trip is basically a coil that sits inside the breaker, and it has a coil that is monitoring the voltage that is coming into the unit. Now, as we all know, in the United States, we have typically clean power, but there are plenty of places that are rural that have power drops coming out of the service provider. And this can cause damage. If you have a 480-volt motor and you're starting to see 400 volts on that motor, you're going to really stress the windings of that. So what this allows you to do is set a level as to monitoring the voltage coming into our breaker. And when it dips below that, this shunt will recognize it and open the breaker automatically. We have auxiliary contacts so that there are ways to bring the switches to disconnect the breaker or open the breaker without actually going to the breaker. Again, a very nice safety feature. You can have it done on automatic, say a time clock. So on a building that you want to shut down the breaker on, say, a Wednesday at 6 p.m., if you have a time that can send out a 24-volt signal to our breaker, these auxiliary contacts will accept that, a dry contact closure, see that now you want to open the breaker, and it opens. This mimics the state of the breaker as well, so we can give you an output, and you can put on a pilot light, which allows you to know if that breaker is open or closed without actually going to the breaker. Again, one of the things here at ABB is we believe safety is our #1 concern, and we're making sure that nobody's going to go into a live breaker situation unprepared and not knowing what they're getting their hands into. Our shunt strip is also available. It's field installable, so you never have to go towards the service power. You can actually take off the face of our breakers, and you can use these low voltage breakers, shunt strips, and what have you to add more product features and fundamental applications can be covered by the shunt strip. So basically, as soon as you flip a switch, the shunt will see the current go through and open our breaker. A bell alarm, again, field installable. Basically, it just lets you know the state of the breaker so that if you're in a remote area, you can hear that the breaker opened and know that the power has been cut down to whatever branch, main, or feeder that you have seen down the line. Again, trying to remove the aspect of anybody going towards the breaker, using the breaker without having the proper, suiting up into a PPE that requires a half an hour, sending a guy out there. We want to make it so that you can remotely tell what the breaker is doing, and we have trip units that actually can tell you why it did what it did. So some of the applications that we have. The UL standards, UL 489, this is the low voltage MCCBs, molded case circuit breakers, and ground fault interrupters. These are for service centers, feeders, branch circuits. It's in accordance with the NEC, the National Electrical Code, and it covers instantaneous trip breakers. Basically, when you're using anything with power and you need a breaker in there, the motor controls always have to have breakers by the NEC. These are the MCCBs are what you're going to be using in your switchgear. We have 100% rated circuit breakers, UL 489. It's unique, which means you can control the loads, which is typically not an application that's recommended for opening and closing that load. So generally, I know it's not the right application, but a lot of people, as they leave their building for the weekend, they want to flip one switch and have everything shut down. These circuit breakers can handle that. It is intended for no more than 80% of its rated current. Again, you don't want to press, that's the guideline I spoke to beforehand. Generally, you want to stay within 80% of the rated current. You don't want to push things to 100%. It'll work, but it's not the safest. It's not the safest way to use the product. Special label is required for thermal testing. We have this available at the T-Max 15 amp to 3,000 amps. So 80% of 3,000 amps, you can be switching under full load a lot of devices. It has a very small frame size for the breaker, which reduces your panels, so you no longer have to have a huge panel in order to control these loads for safety and or just on-off toggle. And we also have smaller conductors. That means less copper, less wires, and a lot more movability. You can get your hands in there to actually attach the conductors to our devices. It's a very big thing for your contractors out there when they have to go and wire these devices into their systems. Another UL standard that we are for is the UL 1066. This is power circuit breakers. Now these are really the heavy duty type breakers. They're for installation in switchgear and switchboard. This is where you're going to have your draw out or your fixed, and it's intended to use with specific adapters or receiver. Typically, you're going to see a cabinet like this that's going to be on your main branches, and these big circuit breakers are going to be controlling different branches going out with those tiny molded case circuit breakers, having the actual feeders to your machines, maintaining the safety and the reliability of the electrical service that are going into the building, out to your branches, and then eventually out to your loads. UL 1558 low voltage switchgear is another UL standard. It contains low voltage powered circuit breakers, switches, instrumentation, and metering, which means that you can see how much voltage is going in, you can see how much current is being used. And I know out here in California where I'm based, it's going to be a huge thing as we get into lead points, Title 24, California Title 24, and eventually the Net Zero Initiative, which will be taking place in 2016. So it's important to know what kind of current, what kind of power, and what kind of voltage you're seeing going into your equipment. There will be rebates based on that, and there will be some kind of punishments, or I guess they call it overage charges when you're using too much power at the wrong times. Service providers love this type of stuff because it allows them to know what kind of service you need, when you're going to be hitting it, and you can report back to any issues that you have. The UL 891 switchboards are large dead front panel, rated for 6 volts or less. This is a little bit less on the power side and more for the critical powers. Basically, it looks like a nice little cabinet with a bunch of switchboards feeding out to all your different equipment. You're going to be using, again, these little T-Max breakers that we have. This allows you, if you do the selective coordinations and your studies properly, to make sure that the breaker closest to the equipment pops first, reducing downtime, reducing cost, and reducing maintenance. This is used in just about every application I can think of, where you have your main breaker here. That's this Emax, which is a huge breaker that's bringing in all the power into there. We break it out into feeder breakers, and then eventually down to your actual branch breakers. Some more applications that can be covered with all these breakers are the UL67 panel boards. And these are devices that convert incoming electric power to smaller circuits. Again, this is overload protection or short circuit protection. They're the high-end fuses. So if you look down here below, this is the NEC requirement for a motor load. So you need to have each one of these devices into the branch leading up to a motor load in order to comply with NEC code. Luckily for us, our breakers do have all these built into them right up to here. So you have your overload, you have your short circuit, you have your disconnect means. So all you really need is a controller, which can be supplied with a motor control unit and an MCU. It can be a simple contactor if you want. And then you have a local disconnect switch, which could be a T-Max breaker, those little breakers that we talked about. You can wrap all this into one simple cabinet that can run several different motors, meet NEC code, and still be UL67 compliant. Industrial control equipment is usually what we're using this kind of equipment for. It's starting, stopping, regulating, and controlling electric motor loads. So you really have a lot of power in this little cabinet here. And as we all know, motors are a big investment. So you can have a $40,000 motor where if an undervoltage hits it and your windings go, that's going to be a lot to replace, not to mention your downtime. A simple product like this with our MCUs, these are our motor controls down here. We have a breaker right above here, complies with the NEC rules, UL67, and it will make sure that your operators and your equipment remain safe throughout the lifetime of the product. So as we talked before, the motor circuit control right here is all inclusive into our T-Max breaker here. So this is a typical setup that you're going to see where you have the disconnect and the short circuit. So this is providing that the LISG curves that we talked about earlier. The power is coming in here, so we're looking for any problems down the line with this motor. Catastrophic problems. So winding breaks and you're starting to short. You're dropping neutral. Somehow your two phases get caught, and believe it or not, I've been out into Arizona on the surface mines, and they talk about all the wildlife that seems to creep into this cabinet, and everything's fine until they cross over phase, and then you need this to make sure that your motor doesn't pop. Right below it, you have the actual controllers. These are the MCUs. Now we have several different type of motor controllers which allow you to do slow ramps, quick ramps, kick starts, all different profiles as far as what your motor requires, torque control, voltage control. So our controls are really, again, a topic for another webinar, but they allow you to comply with the NEC and, believe it or not, extend the life of your $40,000 motor. Voltage case switches, different than a breaker, because the switch is just going to open and close, is also required as a disconnect means above it. It does not provide overcurrent, overload, or ground fault, so you don't have the I protection that we talked about. You don't have the L protection that we're talking about. It enhances, it can be enhanced with the shunt trips so that, again, you can see an overvoltage and pop this. But this is the guy that sits at the very beginning of the chain. So again, if this motor is having a problem, what you hope to happen is that your local disconnect will open it up and cause safety. If not, this overload will see the problem and open up, saving everything back. But if all else fails, you're going to need this disconnect means, which means I have to shut down this whole branch to make there's something really wrong, and I'm going to have to trip to make sure that the current that's flowing through me does not get to my motor or anybody down the line from that short. Some breaker basics on the electrical standards. Now we're going to talk about IEC. IEC 60947-2 is the low voltage switchgear and control gear. This standard applies to the circuit breakers, the main contacts, which does not exceed 1,000 volts or 1,500 volts DC. That's right, the breakers can not only do AC, we also do DC. Again, the DC is very important when you're talking about motor controls. And we cover all the bases with our full line of breakers. Applicable standards, we're not just located here in the United States. Most of the industry is also complying with CE, which is the European UL, if you will. Triple C, which is the China UL, if you will. Most of the time, if you have UL, you're already cleared in all the North American markets. They do carry a CUL as well, which is for the Canadian market, and NOM, which is NOM for the South American market. So that was a quick overview of the breakers as a whole, their functionality. I didn't really get into many of the specifics on the products. We can always, if there are comments, if you need me to come back, I could do another one with just you guys. I believe my email's out there. So if not, it is Edward, EDWARD, Uftring, U, F as in Frank, T as in Tom, R as in Robert, I as in Igloo, N as in Nancy, G as in George, at TNB, that's Tom, T, Thomas, N, Nancy, B, board.com. I want to thank Nicole and EasyPower very much for putting this all together. Again, I want to reach out to all of you and let you know that ABB and the CESs here are ready to help you with any education needs, specific projects, even better. Thank you very much, everybody.